Are y'all ready over there in Germany? Great. Okay, welcome back everybody for the third and final plenary talk of the day. I'm happy to have Akhil Mathew telling us about Syntomic Complexes.
Okay, hello, sorry, can you hear me? Is this working? Can someone wave or something if you can hear me? Okay, great. Thank you. Yeah, thank you very much for the invitation. Yeah, it's a pleasure for me to speak here. Yeah, so I wanted to talk about some a joint project with Bhargav Bhatt, and let me start by explaining some of the motivation for this work. So the motivation comes from the study of the topological cyclic homology of regular rings in mixed characteristic. So the motivation is to study TC of regular rings or regular schemes in mixed characteristic in particular. And this is a subject that has been studied extensively in the literature before, and so in particular in the work of Hesse-Holt and Madsen from 03 and 04. So this has been studied before by Hesse-Holt and Madsen. So for smooth algebras over a DVR. And in their inspiring papers, they really make the connection between topological Hochschild and topological cyclic homology and the structure on them, and mixed characteristic algebraic geometry, especially through the de Rham-Witt complex and certain generalizations of them. So the motivation for this project, oh sorry, I should not write this too low because, okay, maybe it's okay. So the motivation for this project was somehow to revisit and also extend some of their results using some of the remarkable advances in the subject that have taken place in the past few years, in particular the Motivic spectral sequence for TC developed by Bhatt, Morrow, and Schulze. Yeah, so maybe let me start with by describing some background. So motivation for this Motivic spectral sequence in particular. So I think some of the motivation comes from the following construction or theorem. So this is due to Friedlander-Suslin, Levine, and Voevodsky. And this construction gives a spectral sequence. So let X be let X over K be a smooth quasi-projective, I'll just say smooth variety. So then you can consider the algebraic K theory, the algebraic K groups, or the algebraic K theory spectrum of X. And then the statement is that there is a spectral sequence which starts from the Motivic cohomology, in weight J and degree I, and converges to the K groups, K 2J minus I of X. So this is called the Motivic spectral sequence, and it comes from a filtration at the level of K theory spectra. Right, so this was originally, I think, envisioned as an analog of the Atiyah-Hirzebruch spectral sequence in algebraic topology, where you have topological K theory of a space, and you have a spectral sequence from singular cohomology. And I just want to say a little bit about the left-hand side, these Motivic cohomology groups. So these HI mode were, so we'll just say left-hand side, Motivic cohomology. This was originally defined by Bloch. So this was defined first by Bloch under the name higher Chow groups. And Bloch writes down an explicit complex of algebraic in terms of algebraic cycles on X and products of X with affine space. And so in particular, from that point of view, it's very clear that the Motivic homology is somehow a generalization of the theory of the Chow ring for a smooth variety. Okay, but this is an explicit but very complicated complex involving like all algebraic cycles somehow. And you can also think about it more categorically in terms of this category DM, this derived category of motives. So it's also left-hand side is also, well, it's representable in the category DM, this derived category of motives. It's essentially maps from X. It's maps from X into Z of J in this category DM of motives. Right, and so it turns out that this tells you a ton of information about K-theory, especially with mod P coefficients. So this Motivic spectral sequence gives you tremendous information about K-theory after profinite completion, because it turns out that after profinite completion, one can give a complete description of Motivic cohomology. And that's the following theorem. So this is a theorem which is due, well, I'll explain so let me explain the attribution. So it's due to Geisser-Levine and Voevodsky and Rost. So the theorem is that if you take these Z of J's, if you reduce them mod P, so if you take Z mod P twisted by J, and maybe just to emphasize, I'll write it as Z mod P of J mote. Well, these form complexes of sheaves in the Nisnevich topology. And you can give a formula for them of what they are in the Nisnevich topology very precisely. They're given by the truncation in the Nisnevich topology, truncation in cohomological degrees at most J, of their Atoll sheafification. So you can recover them from their Atoll sheafification as truncation in the Nisnevich topology. And furthermore, you can say exactly what this Atoll sheafification is. So here, so this Atoll sheafification, well, there's sort of two different cases. The first case is when P is not 0 in the base field. So if P is not 0, it's given by mu P tensor J. It's the usual Tate twist. So if P is not 0, and if P is equal to 0, it's given by this complex omega J log shifted minus J in characteristic P. And so here, omega J log is the subsheaf of the sheaf of differential J forms, consisting of sheaves that are, it's a subsheaf generated by D log forms. So it's generated by things that look like dx1 over x1 times times dxj over xj, at least locally in the, let's say, Nisnevich topology. And sorry, about the attribution, so the case when, well, I guess the case when P equals 0 is a theorem of Geisser and Levine. And I guess that's closer to what I'll be talking about today. The case where P is not 0 is due to Voevodsky and Rost, and it was the Beilinson-Lichtenbaum conjecture. Right, so this gives a very sort of complete description of these motivic complexes. And it gives you a lot of control over the K-theory spectrum after profinite completion. So for example, it tells you that if you have an algebraic variety over the complex numbers, then its p-adic algebraic K-theory coincides with the p-adic topological K-theory in sufficiently high degrees. Essentially because these truncations sort of stop mattering once you're in sufficiently high degrees by some cohomological dimension basis. Okay, so this is maybe kind of the background motivation. But notice that in this theorem, it's really essential that you have a smooth variety over a field. So I think sort of a natural question here. So is there an extension of the spectral sequence and of the left-hand side? So is there an extension of the above to more general situations? So that could mean singular varieties over a field or schemes in mixed characteristic, to singular or mixed characteristic settings. And there are a couple of obstructions, at least using sort of similar methods in this context. So one obstruction to doing this is that if you, for example, if you look at Bloch's definition of higher Chow groups, I mean, in terms of algebraic cycles, these don't see nilpotents because these don't see, yeah, I mean, they're in terms of algebraic cycles, and so they don't see, somehow they don't see nilpotents. And somehow relatedly, okay, so let me just say it this way. So right, so algebraic cycles themselves don't see nilpotents. And another is that a lot of these methods, and so for example, I mean, the subject of A1 homotopy theory, it's really based on A1 invariance. So invariance when, so you have some construction and it should give you the same answer on a ring R and to the ring adjoining a polynomial generator. And the issue is that A1 invariance fails for the K theory of non-regular rings. But I think already, for example, there isn't, at least in the full generality of regular schemes in mixed characteristic, where this obstruction is not there, there isn't sort of a full analog of this picture. Okay, but so I think this is a natural question somehow. And let me mention that there is some work, ongoing work of, in this direction, of Bachmann, Elmonto, and Moro. And this is in the case of FP schemes and really, I think, p-adic K theory. Okay. So I guess in the past few years, there is a construction, there is an analog of this construction that somehow works very generally in the world of TC. Sorry, I guess I can write on this board. Okay, so there's the construction due to Bott, Moro, and Schulze of an analogous spectral sequence or filtration for topological cyclic homology. So the construction is that for, let's say, R is any ring or even animated ring, say R is any animated ring. And let me assume it's P complete, because what I'm going to say is not going to be affected by P completion. So let me say P complete for simplicity. So then there is a spectral sequence or a filtration which goes from an object called a Syntomic cohomology of spoof R with coefficients in weight J, and converges to TC, again in the same, with sort of the same indexing, 2J minus I of R after p-adic completion. So there is an analog of the Motivic spectral sequence in the world of TC in this work of Bott, Moro, and Schulze. Yeah, so let me comment that this construction, so if you compare with the setting of K theory, this is defined very generally. It's defined for any animated ring, and that's because somehow the construction of Bott, Moro, Schulze is very direct. I mean, essentially, it's based on just take a Plotnikov tower in a suitable topology called the quasi-syntomic topology. So it's somehow a very robust construction, and it works with arbitrary singularities. So for that reason, it can be defined sort of very generally. And let me also mention that, so recently, well, very recently, this has been extended to a large class of ring spectra. So a new construction of this spectral sequence and filtration was given, and in fact, the new construction works for a large class of ring spectra. So the remark is that this has recently been extended in work of Hahn, Braxton, and Wilson to ring spectra. So they construct an analog of this spectral sequence, and in particular, they define an analog of syntomic cohomology in this context. Okay, so now I want to say a little bit about what is syntomic cohomology. So the subject already, right? So what is syntomic cohomology? So this came up a bit in Ben Antio's talk on Monday, but I want to say a few more things about it. So right, so as Ben mentioned, syntomic cohomology is a construction that can be defined in terms of the theory of prismatic cohomology. It's a sort of filtered for, there's a formula for it as a sort of filtered Frobenius eigenspace of prismatic cohomology. You can also define it, I mean, another way you can define it is, I mean, you can define this filtration, you can abstractly define the filtration via this general construction, or using the the construction of Hahn, Rexford, and Wilson. And then, well, you can say that syntomic cohomology is the associated graded terms of that filtration. I want to say a couple of other things about syntomic cohomology that are maybe a little bit complementary, that might be helpful. So one is, right, so one is that the idea is that syntomic cohomology is supposed to be an analog of p-adic Atoll Motivic cohomology. I mean, I sort of hinted this, that makes sense in this in very generally. So idea is that syntomic cohomology is a general form. It's a general and somehow a synthetic form of p-adic Atoll Motivic cohomology, and well, in a sense I'll explain. Sorry, it's a general form of p-adic Atoll Motivic cohomology, let's say for p-adic rings. And part of the motivation for that comes from the fact that TC is essentially p-adic Atoll K-theory for p-adic rings. In fact, for p-adic rings, TC is essentially, well, essentially meaning on connective covers, is p-adic Atoll K-theory. So you think of, well, one can think of the spectral sequence as being some Atoll version, Atoll sheafified analog of the Motivic spectral sequence, which maybe a priori in this generality has not yet been constructed. Okay, so this is one idea. And another idea is that there's this, so I want to say the following way that one can think about it. So there's this emerging picture. I mean, I'm calling it an emerging picture because not all the translations have yet, I think, appeared in the literature. And this is due to the work of Drinfeld and Batlury. And what this work, so okay, so the emerging picture is that there is a stack, there's a certain object, there's a certain object, certain sort of remarkable object called sigma double prime. And this object is a type of stack. So essentially it's a functor from rings to groupoids, and it's a functor that you can write down by a formula. So which is an algebraic stack defined by its functor of points as a functor from, let's say, p nilpotent rings to the category of groupoids. And this object is sort of remarkable in the sense that if you take the derived category of, let's say, the derived category of quasi-coherent sheaves on sigma double prime, is that this is supposed to be some analog of the theory of the category Dm, of the category Dm, the derived category of motives. So this is some analog of, well, everything is in some p-complete world, but it's some analog of the category Dm, the derived category of motives. But it's an analog of dm in a very different sense, because dm is somehow defined in terms of algebraic cycles on varieties. Whereas this is an object that's defined in a completely different fashion. It's defined in a synthetic fashion in that it's just defined explicitly as a functor on rings. And I will at least tell you a little bit about a piece of sigma double prime. But yeah, let me say a few more things. So second, what I should say is that to say more about this sort of analogy with dm, if I have a p-adic formal scheme X, then this is going to give rise to an object which I'll call H prism of X, which lives in the derived category of motives. Just as a variety will define a class in dm, or in some category of motives, this is going to live in the derived category of quasi-coherent sheaves on sigma double prime. And roughly speaking, this is the prismatic homology of X together with its natural structure, so as defined in the work of Bode and Schulze. Okay, and so furthermore, you can describe syntomic cohomology. So syntomic cohomology is supposed to be like Motivic cohomology, which should be representable. So in fact, syntomic cohomology is naturally cohomology on the stack sigma double prime. So, well, I should say that there are objects. So first of all, well, syntomic cohomology has all these different weights. And in fact, there are objects. Well, I guess I should say there are objects in the Picard group of sigma double prime called the Breuil-Kissen line bundles. So these are called Breuil-Kissen twist. And these are objects that somehow play the analog of Tate twists in this p-adic world. And furthermore, then the syntomic cohomology of X of p-adic formal scheme X. It's given as the coherent cohomology on sigma double prime of H prism of X. So this is roughly something like the motive of X, and then you tensor it with this invertible object O twisted by J. Okay, so I don't want to actually define sigma double prime. So I would refer to the paper of Drinfeld titled Prismatization. But let me at least give the definition of sigma, which is what Bott-Lurie called W cart, and which is a piece of what goes into sigma double prime. And so the definition is that sigma of R. So sigma is a functor from p nilpotent rings to groupoids. So if R is a ring which is p nilpotent, then sigma of R consists of the following data. So it's the groupoid of, first of all, you have to give an object L, which is an invertible. So it's an object of the Picard group of W of R. So it's an invertible module over the ring of bit vectors of R, plus a map from L to W of R, just a map of W of R modules. So in other words, it's a virtual Cartier divisor on this ring of bit vectors of R. Such that this virtual Cartier divisor becomes a divisor P after any base change to a perfect field. After from R to a perfect field, this recovers P. So in other words, it's a virtual Cartier divisor, an invertible module over W of R, and a map to W of R, which is in some sense a deformation of P. Which is, so this is in the principle of prismatic cohomology, where somehow you're considering deformations of P. But so this is an explicit functor from p nilpotent rings to groupoids. And sigma double prime is an elaboration of this that in particular allows various degenerations of this type of configuration. Okay, but in particular, it is very explicit. And what's kind of remarkable about this picture is that sigma double prime is something that can be studied explicitly, because it's given by some formulas, and you can really study the geometry of the stack. So in particular, there are various loci sitting inside sigma double prime And while sigma double prime is rather large, there are various loci that can be described really explicitly. So and this has been studied by these authors. Okay. Okay, so this was mostly motivation. So what I wanted to talk about is essentially a description. So this is some motivation for syntomic cohomology. And what I wanted to talk about is a description of the syntomic cohomology in the case of regular rings. And so by this Motivic spectral sequence, this is closely related to what I started the talk with, which is a question of trying to understand TC of regular rings. So the goal is to describe the syntomic cohomology somewhat more explicitly. For regular p-torsion-free rings. Okay, so to state the result, I need to use the following construction, which somehow plays an important role in integral p-adic Hodge theory, which is this construction of a comparison map. So there's the following construction. So let R again. So R is going to be any p-complete animated ring. So let R be any p-complete animated ring. Then there's a comparison map which goes from the syntomic cohomology of SPUF R. And so I'm going to state these results really with mod p coefficients, but they also have the natural analogs with mod p to the n coefficients and p-adic coefficients. So let's say the syntomic cohomology of R with mod p coefficients, but in weight j, and this maps to the Atoll cohomology of the generic fiber. Well, you could consider it as some sort of rigid space or adic space, or here just as a spectrum of a ring. And it goes to the Atel cohomology of the space with Tate twisted by I coefficients. So it goes from the syntomic cohomology with weight j to the Atel cohomology with weight mu p, well, again with weight j. So this type of comparison map plays an important role. Sorry, I hope this is visible. But anyway, so this type of comparison map plays an important role in p-adic Hodge theory, because over here you have syntomic cohomology, which is in some sense it comes from various elaborations of de Rham cohomology of the ring. And on the right-hand side, you have the Atoll cohomology of the generic fiber. And this comparison map is saying that these two sort of talk to each other. There's a map from the invariant that's defined in somehow in terms of de Rham cohomology, mapping to something in terms of Atoll cohomology. Right. So there is such a map, and for example, there's an account in the paper of Bad and Lurie, absolute prismatic cohomology. But in fact, so in fact, you can sort of say it. I mean, one way to think about it, which I like, is that, I mean, if you think about syntomic cohomology as a type of Motivic cohomology, then this is just a map that you should get from functoriality, from the Motivic cohomology of R or to the Motivic cohomology of R joined 1 over P. Let's say a Tel Motivic cohomology. So you should really expect a map like this. And in fact, you have to do some work because these are defined in sort of very different ways, but one can sort of write down such a map. And one thing that's really nice also about this theory, and in particular about this integral theory, is that this map has a very nice description. And that's the following theorem, which is called the Atel comparison theorem. So there's the following theorem, which is, again, so it's the Atel comparison theorem. Judabad and Schulze. And it states that that map, this comparison map from Syntomic cohomology to Atel cohomology, is essentially a localization map. So again, these two sides are defined in very different ways. But somehow you have a map, and the map is in fact localization. So the comparison map exhibits the target as the localization of the source at a particular class called V1 living in the Syntomic cohomology of SPUF ZP with coefficients in weight p minus 1. So in the Syntomic cohomology of ZP, there's a class with mod p coefficients. There's a class in weight p minus 1 called V1. And I'm calling it that because it corresponds to the class in stable homotopy theory called V1, if you think in terms of Motivic filtrations. Though in fact, you can construct V1 in this prismatic context sort of purely directly as well. But so there is this class V1, and the statement is that once you invert V1, that's exactly what the map from Syntomic cohomology to Atel cohomology is doing. It's exactly inverting V1. So this is called the Atel comparison theorem. Okay, and so now I guess I can state the theorem that we prove. So our theorem right, so it's about the Syntomic cohomology of regular p-torsion-free rings. The Syntomic complexes are Atel sheaves. So I will just describe their stocks. So if R is p-torsion-free, regular, and strictly Henselian, then the statement is that this comparison map from Syntomic cohomology to Atel cohomology of the generic fiber is essentially a truncation. So then the map from H star Syntomic of SPUF R with weight J to the Atel cohomology the theorem is that this is, well, right, so this is an isomorphism for star less than J minus 1. It's injective for star equals J. And you can also describe the image. So the image is essentially generated. If you consider the Syntomic cohomology or Atel cohomology as a bigraded ring, it's essentially the part that you know has to be there coming from the generators in degree 1. So you can describe the image in H. So the image is an HJ Atel of spec R adjoin 1 over P with coefficients in mu P tensor J. It's the image is the objects that come from units in R. So as the image of the symbol map, or the Kummer map, well, essentially the Kummer map, from R cross tensor J. So if you have a unit in R, that defines a class in here for j equals 1. And then you can take the cup product of those over all j. And so you know those have to be in the image. And then the statement is that that's exactly the image. And in fact, so that's the theorem. But let me also add that the source actually lives in degrees at most j. So this is in work of work with Antio, Moro, and Nicolaus. The source, so the Syntomic cohomology, lives in cohomological degrees cohomologically. So this is actually telling you what all the Syntomic cohomology groups of R are in terms of the Atel cohomology of the generic fiber. And moreover, from the way it's set up, it's actually a description in the level of the derived category. It's the Syntomic R gamma Syntomic is a truncation of the R gamma Atoll, and then you sort of modify it in the top cohomological degree. So this is the description that we give of the Syntomic cohomology. Yeah, so let me say a little bit about the related work. So right, so the first thing I should say is that this construction of taking the Atel cohomology, modifying it, truncating it, and modifying it in the top degree is originally appears in work of Schneider. And it was also studied by Geisser. So Schneider was working with smooth schemes over a DVR. And it was generalized to semi-stable schemes by Sato. So this particular truncation construction had appeared before, and we're sort of identifying it with the Syntomic complexes. And also, so many special cases of this result have been proved in the literature previously. So I won't go into too much detail, but there is a prior approach to Syntomic cohomology before BMS2. Which was originally due to Fontaine-Messing and Kato that used Theorem cohomology instead of prismatic cohomology. And it doesn't quite, it gives the right answer in either in low weights or if you work up to isogeny. And so using that earlier approach to Syntomic cohomology, so let me just say that many special cases were proved by Kurihara, Kato, Tsuji, and Kolmaz-Niziel. I think using the different methods. Okay, so I have about 7 minutes. So let me say a little bit about the methods that went into proving this theorem. So the methods that went into proving this theorem were really inspired by algebraic topology. So in fact, so in fact, everything can be phrased purely algebraically. So in our paper on the archive, everything is phrased purely algebraically without any mention of THH, because everything can be formulated prismatically. But in fact, somehow the approach was really inspired by algebraic topology, and in particular was based on the Sigel conjecture, or an analog of the Sigel conjecture. So I thought maybe I can explain that. So the Sigel conjecture, well, I should say the Sigel conjecture in THH, so the motivation why this is called the Sigel conjecture is that for CP, the Sigel conjecture states, so the Sigel conjecture, which is a theorem of Gunnar-Wardena and Lin, states that the sphere spectrum is, after P completion, is the same thing as its own Tate construction. So the CP Tate construction of CP acting trivially on the sphere spectrum is the P-complete sphere spectrum. Which is a really, I think, really remarkable fact. And it's been observed by many authors that there are somehow analogs of the Sigel conjecture in THH. So the Sigel conjecture for THH is a statement. So there are many such statements in the literature. This is the statement that THH of R, well, if you have THH of R, then by the cyclotomic Frobenius, this maps to the Tate construction, to its CP Tate construction. And let me P complete everything. And the Sigel conjecture for THH refers to the statement that this type of map is an equivalence, usually not an equivalence directly, but an equivalence in high enough degrees. So it's the statement that this map is an isomorphism in high enough degrees. So, right, and so I guess it's been observed, many times in the literature that in a lot of cases this type of statement often holds. And right, so the connection is that if you were to plug in R being the sphere spectrum, then you would recover precisely this statement. I mean, well, then the cyclotomic Frobenius would be exactly would be an equivalence, and it's a statement. Okay, so essentially what we observed. So we showed, well, somehow the main ingredient in this theorem is the observation that a regular ring satisfies an analog of the Sigel conjecture in the sense on THH, but on the level of associated graded terms with respect to the BMS Motivic filtrations. So we showed that if R is regular, then the map from THH of R CP to Tate CP is somehow it's sufficiently co-connective on associated graded terms, and in sort of a precise quantitative sense is co-connective on associated graded terms with respect to the BMS Motivic filtration in a somehow a precise sense. And so actually this is something that you can, so we gave a definition. So one is that this is a definition you could say in the language of prismatic homology, but essentially it comes from thinking about, or it came from thinking about the cyclotomic Frobenius on THH and the Motivic filtration. But we gave this a name. We call this condition on a ring F smoothness. And then something that we showed is that well, F smoothness is, for a Noetherian ring, F smoothness is equivalent to regularity. In general, F smoothness can be thought of as sort of a mixed characteristic analog of the Cartier isomorphism for smooth FP algebras. And so somehow in this mixed characteristic setting, smoothness gets replaced by regularity. Right, so so what else should I say? Right, so essentially, the strategy is that you have to combine, you have to use this F smoothness, but then also use the Atel comparison theorem, which I've now erased, that gives the relation between Syntomic homology and Atel homology in general, and also use this sort of filtered Sigel conjecture for regular rings. So there's a little bit of linear algebra involved that I won't get into. Since I have just a minute and a half left, maybe let me end with a question, which would be. So let me end with the following question. So right, so here we obtain this description of, so in this work we obtain a description of Syntomic homology of p-torsion-free schemes in a sort of explicit form. And again, the idea that I was starting the talk with is that Syntomic homology is some sort of analog of p-adic Atel Motivic homology. And as I mentioned, there's a theory, if you have smooth schemes over a field, there's a theory of actual Motivic, of Misnevich Motivic homology, the thing that filters K theory instead of TC. And then there's a way of relating Motivic homology and Atel homology, which is given by these sort of these truncations, Bell's-Lichtenbaum conjecture. And so the question is there a theory of of Motivic cohomology of regular schemes and mixed characteristic such that the Motivic complex is again given as some sort of truncation in Linus-Navitch topology of the Syntomic complex, which is described here. So essentially the question would be to have some sort of mixed characteristic analog of the theorem about Motivic cohomology that I mentioned for smooth algebras over a field. So let me mention that this is known by Geisser for smooth schemes over a DVR. But I think it's an open question in general. Sato also raises this as a question in a semi-stable case. Over time, I just want to I forgot to mention, so I mentioned that the Sigel conjecture plays a role in this, but I also want to mention, again, that this is somehow not a new idea. The Sigel conjecture plays an essential role in, I think, all prior work on the subject, in particular the work of Hesse-Holt and Madsen. And essentially what we do is to sort of combine that with the Motivic filtration. Okay, so I'll stop here. Thank you very much.